Greetings and welcome to the RC Wall Vacuum channel. In today's video, I'm going to cover a couple of interrelated subjects. The first primary, the primary one is going to be the failsafe kill switch prototype I've been working on. I finally got the board layout done, as seen on the screen there, and I now have some small little PC boards for it. I wanted to shrink it down a little bit smaller. Primarily, I wanted to see how the electronics going to respond being tighter packed with the EMI coming off the Taylor coil. And so I wanted to test that. And the interrelated subject is this kill switch project is just the first in a series of electronic modules I want to build for these fifth scale gas-powered vehicles. Most of them are going to revolve around the concept of a wireless SCADA system. SCADA means supervisory control and data acquisition. The first modules I'm working on right now are going to be mostly data acquisition off the engine, but I will have future modules that will have supervisory control, and especially when they tie in with the kill switch and an accelerometer. So for today's video, I'm just going to give a quick preview of that particular module, and then I will go back to assembling this, and I have it rigged up over here to run through the test of the kill switch, and check that out. So let's go check out the future project. So what I have set up over here, like I mentioned, it's going to be a wireless data acquisition system off the engine, off the engine parameters. And what I got going now is I got two separate modules. This module here would be mounted, obviously it would be packaged differently, but this would be mounted in the actual chassis of the vehicle. And I will be welding this particular part into the Taylor pipe, so that I can put this EGT exhaust gas temperature sensor into the pipe, and it's a Type K thermocouple. Then it'll be coming back and be fed into one of these thermocouple amplifiers. And then I'll be monitoring the cylinder head temperature off of this ring here, which is also a Type K thermocouple, and it will be also going through one of those amplifiers. It'll be fed back into the microcontroller's analog input. This whole thing will be running on a chassis off the LiPo. And so I will be also be monitoring into another analog input the LiPo battery status. And then the fourth input is going to be coming off the RPM. I'm going to probably put a Hall effect sensor, if I can fit it in there, on the read to magnet on the flywheel. And then that'll come back as a digital input into the microcontroller. And then all that's sent through these little wireless modules here. I don't know if you can see it from that angle. It's also pretty low power, but even with the low power, it still can transmit quite a ways. I think a straight line is good for 5 to 10 miles, but you start getting anything interfering and it starts to cut down. But certainly, it definitely will have no issue on track size dimensions. So back at the pit, there would be this ensemble. Obviously, be packaged differently. But it's going to have the receiver and then the microcontroller, and then I'd have you probably won't be able to see it, but there is some text being displayed on that OLED. It would probably be a bigger display on there, plus I'd have a keypad to set parameters and things like that. And also in the pit module would be an SD card reader, kind of along the lines of this. And all the data would go in as a CSV file. So you'd be able to link up to your RPMs and cylinder head temperature and EGT temperatures all at the same time for tuning purposes. So right now this display is actually showing the voltage that's over on the transmitter board. I just have a potentiometer tied into the analog input, and it's getting converted and then sent to this particular unit. As you can see right there, that's the unit with a little potentiometer in there. That's the transmitter side. So one of the upgrades I'll be doing is I get this part of it developed, will be to put in a little module like this. This is a small GPS module. I don't know if I would use that particular one. I have to test it first, but the whole point would be to give you a wireless speedometer back to the same base station, so you can read your speed right there at the pit. So I have to develop this stuff in stages. There's a lot to do it. Speed's going to be an issue. When you start trying to get a speedometer of sending back real-time speed, processor time starts to be an issue. So I'm not 100% certain whether these wireless modules are going to be able to handle the baud rate of that, but that's all going to come through testing. But certainly they're going to be more than sufficient for the initial data acquisition for the engine management. Well, my first go around in RC back in the early 90s, it was all kits. Traxxas was just starting to come around, but even those, you had to, for certainly had to paint the body. I don't remember when I first got my nitro buggy, whether I had to assemble that or not. I know I had to paint it. But I got out of it for quite a few years, and then when I came back in here recently, the first thing I noticed is there is no kits. I mean, there's a couple kits, but it's mostly all ready to run. So kind of what I'm angling to with these modules is kind of a little nostalgia to go back and start doing some kits. So I'm toying with the idea of actually doing these modules as kits and supplying the boards and the programmed microcontrollers and the bill of materials and video instructions on how to put it together. So that's kind of what I'm shooting for here, and we'll see how that goes. I got a lot of testing and a lot of developing. Unfortunately, I don't have a lot of time to do it with, but I get done what I can get. So if you're interested in stuff like that, keep checking back and see how far I get on that one. So in the meantime, let's go back and check the kill switch out. So in a previous video, I went over the theory behind what I'm trying to do here with this and my less than stellar experience with some other manufacturers' kill switches. I'm sure someone out there is making something similar to this or something that does the same principle, but I just prefer making my own. So I'm not knocking anybody else's design or nothing like that, but the whole point of this thing is that I want as close to fail-safe as you can get. To me, having a runaway vehicle is kind of unacceptable. I mean, there's a lot of issues. People can get seriously hurt if one of these hits someone. In my particular case, my track's located far enough from civilization, it would probably run out of gas before it hit anybody, but still a lot of trees I can hit, so I'm trying to avoid that. So anyhow, what I ended up doing is I did a layout on a program called KeyCAD, and it's an open source program, works pretty good. If anybody interested in doing a board design, I highly recommend looking into it. It's a cool program. I think I'm on version 7, but there's a version 8 out now. On the right hand screen there, that was the original board layout, and then the manufacturer requires these things to be panelized, and then over here on the left side is the panelized version. That's what you end up with, and it's really meant for ease of manufacture, and especially if you're going to be going to a pick and place machine, you need somebody. In my case, that doesn't matter. I'm just hand soldering these things in place. So I've already got two assembles here. I got this one's going to be going into Kraken, and giving it a run up there, and I got the box already made for it. And over here on the breadboard, I have another version wired in that I can put into a breadboard and actually tap out the circuitry to give a demo of how this thing's working. So let's take a look at that. So in this melee of wires and components, this right here is the actual board. And I had to do some for demo purpose, I had to do some reconfiguring and invert the logic on the output because being normally closed. And what I'm using to simulate the engine is a little buzzer. So I had to invert the logic to get this thing to work for demo purposes. I won't bother to explain that, but that's why it's like this. So let me give this thing a fire up and we'll run it through its tests. So I'm using a Spectrum 6200 radio receiver in there and then their DX5 transmitter. To power it right now here on the bench, I'm just using this lab supply, and I got it set to 8.2 because I figured it's probably a fairly well charged LiPo. So when and then I do have I got it set in there, so it's around 7 volts. It should drop out and shut down if your battery starts to drop out. So we'll give this thing a fire up, and you should see a sequence of lights appear on the board itself. So let's give it a try, and it should end as a red. So there's a fire sequence on the kill switch, and the receiver's done its boot up, and we should be ready to go. So we got no buzzers, so that means no engine. Because if you hear the buzzer, that means the engine's capable of running. So I have aux D set on my radio, so we'll give that a kick up, and we should see a green light and hear a buzzer. All right, so right now we're ready, able to run. Hit the kill switch down, drops off, so we're good there. So let me get it kicked back up and operational, and then I'll simulate it losing any kind of power or any kind of signal coming in from the receiver. So I'm just going to cut the power. All right, so it automatically kills it, and then it'll stay even if it was glitching, it'll come back up, and it shouldn't come on. Yeah, no, it definitely does not come on. until you actually hit it again. So then for next time, I'm going to simulate the battery voltage dropping out and see how it responds. Run through a sequence. All right, it's ready to go. All right, we're operational, and I'll start bringing the voltage down. And I'm about 7.1. Right there, about 7.03, it drops out. I can change that in software, but I'm going to leave it like that. And that drops out everything, and there's your diagnostic LED to tell you your battery's got an issue. So I don't know if you could tell in the camera, but the low battery was a kind of a purple color. I'm going to run through, show a signal loss coming off the receiver. Fire this thing back up. Get her back into operation, and I'll pull the signal line here. And I don't know if you can tell that, but that turns into a flashing pink. And there is a little different pulse rate, I believe. I think I put that in software. I don't remember offhand, but they're definitely different colors. So a pink's going to be loss of receiver, and purple's going to be low battery voltage. And even if you come back with your receiver, it's locked out. Once this thing triggers, it's locked out. You have to recycle power to bring it back up, and that was done intentionally. So for anybody who's curious how these kill switches interface to your radio receivers, up here on the scope I have it's all with pulse width modulation, and up here on the scope I have displayed right now. This is at the idle mode, and the vertical divisions on the scope are set for 500 microseconds. So as you can see, there's a 1500 microseconds, which is also equivalent to 1.5 milliseconds, but that is the idle signal. And that's what I'm looking for under normal operating conditions. After it gets this, that's the start, which is 1100 microseconds. And so now we're running. So when I shut it back down, it goes to 1900 microseconds. And the way I got this set is when it looks for that, I'm holding the button up right now. Even though it's showing green, it's not actually firing the relay, and it's still holding that 1100 microseconds. So it sits there in software and waits till the 1500 microseconds comes in. Then it knows it's got a clear signal from the receiver, and you're good to go. So once it's initiated, and if it doesn't see that 1500 microseconds, shut that off. It doesn't see that 1500 microseconds, it just shuts everything down. Or if it sees a 1900 microseconds, or it loses power, or the microcontroller locks up, whatever the case may be, MOSFET blows, whatever, the relay is going to slam close, and it's going to shut the engine down. That's hopefully gives you the close to the failsafe as I can get. Now, as far as the relay goes, I'm using a little tiny reed relay, and normally those are only good for low voltages, so I had a little bit of trouble finding one to handle the high voltage that coil puts out on the trailer. It's around 150 volts, I believe. This relay goes up to 200 volts, and it actually has a high shock rating. I want to say it's around 50 G. I forget offhand what it was. It should be plenty high even for my bad driving. And these don't use spring returns. Everything's magnetic in there, so you don't have to worry about parts breaking off like you might have to in a mechanical spring setup. So I'm hoping that also adds some more fail-safe to it. So here's the final assembly that it's going to go up in the Kraken. Like I said, I got the little 3D box printed. It says it's going to wire tie down onto the front end of the unit for now. And so it drops in here. Cover snaps down in there. Some cutouts for the wires in the back and off the side. And I'll just get wire tied in. The LED sticks out of there. And like I said, this gets wire tied around. Goes to the front tie plate. I forget the thing's called on the front end there. But that'll be located there. And this will feed into the new receiver battery box I put on there. And should be good to go. So it's still too muddy and crappy out there to go out and test it today. So check back, and as soon as we get some better weather, I'm going to go up and load this thing in, the new kill switch in there, and go up and give it a test on the hill climb with a tracker, or maybe both. But in the meantime, thanks for watching, and feel free to subscribe, comment, like, whatever.